Okay, so last time we finished up chapter 2 finally. A reminder, as I mentioned a while back, I did post a lecture for chapter 3. So just to kind of keep us on pace with the upcoming holiday coming up on Monday, I think it's a holiday. So do not show up. Chapter 3 is up there. You are responsible for it. So look it over. Obviously, if you have any questions on chapter 3, I'd be more than happy to answer those. You could ask during discussion. I'll be happy to do that. So kind of keep us four. So once again, though, you are responsible for chapter 3. So make sure you take a look at that video. It's just, I think it's less than an hour, maybe, or something like that, maybe. All right. So in chapter 4, we're going to talk about a lot of stuff. We're going to talk about, I don't remember, but we're going to talk about atoms. We're going to talk about elements, I think. We're talking a little bit about how the sort of structure of the atom was sort of discovered. We'll talk about some parts of the atom, protons, electrons, and neutrons. We will also talk about electron configuration, which is kind of a big part of this chapter. And I think that should be all of it in this chapter, I think. All right, so let us get started then. Atoms and elements. So really, the basic unit of any element are atoms. So remember that elements are really as far back as you could go. So they're sort of, the basis of everything that is sort of put together in compounds and molecules. And really the basic unit of any element are atoms. And atoms, as we'll talk about, really contain sort of 3 parts to it. Although atoms are really, really small, they do contain protons, which, as we will see, are positively charged particles. They do contain electrons, which are negatively charged particles, and they do contain neutrons, which have no charge. So we have these really small things, which are atoms, which are the basic unit of all elements, and within that they're sometimes referred to as subatomic particles, made up of protons, electrons, and neutrons. So when we talk about elements, oftentimes we do refer to the elements a lot of times with their symbols. So on the periodic table, for example, you can find the symbols for all the elements that we have. Now, some symbols are 2 letters and some are 1 letter. And if it is a 1-letter sort of symbol, you always capitalize it. And if it is a 2-letter symbol, the first letter is capitalized, the second one is not. So like aluminum here, where the symbol is Al, we want to capitalize the first one and not the second one. And that's really important when you write symbols for elements, that you do not write everything perhaps in capital letters. So for example, if you wrote CO versus C capital O, there is a difference between these 2 things. The one on the left is cobalt, which is an element. The one on the right is carbon monoxide, which is not an element. So they are very different things. So if you're somebody that writes things kind of all in capitals, you definitely do not want to do that. When you are writing symbols for elements, you want to always capitalize the first one, again, lowercase the second one there. Now, what are elements? Elements are really pure substances that cannot be broken down any further. So you can think of like the periodic table there. Those are all the elements we have, 100 and whatever it is up to these days, 18, 16, somewhere in that ballpark. But they're really as far back as you go. You can kind of think of them as like the alphabet. There's only 26 letters, but different combinations. Obviously, letters gives us different words. And same idea, different combinations of elements gives us different compounds. And depending on even the same sort of combination of elements, but different amounts of the same elements, can give us some different compounds, different than what we might see. So when we talk about elements, and we might have touched upon this maybe in chapter 1, but just in case we didn't, we have elements, and elements can be combined to make molecules or can make compounds. Yes, that's a way to do it that way. Now, these are two words that, again, sometimes people get a little confused, sort of what is the difference between these two, molecules and compounds. So a molecule is just basic definition of two or more atoms together. So if you say you have a molecule of something, that is really just saying I have two or more atoms together. They could be two atoms or more of the same element. They could be two atoms or more of different elements, but those are molecules. A compound, on the other hand, which we might see down the road here, is the combination of two or more elements or atoms of two or more elements coming together. So there are certain elements that do come as molecules. So common ones is H2, hydrogen gas, nitrogen gas, oxygen gas, fluorine, chlorine, bromine, and iodine. So these guys are what are referred to as diatomic molecules. So those are diatomic molecules, and basically diatomic molecules mean that there's really two of them. Di means two, atomic means atoms. So how hydrogen normally comes when it is basically by itself, it's not combined with anybody else, is that it comes basically as two. So it's basically two hydrogen atoms together. Oxygen, same idea. Oxygen comes as two oxygen atoms that are bound together. Nitrogen, same deal. Nitrogen comes as basically two nitrogen atoms together. So if you have any of those sort of whatever that is down there, 3, 6, 7 of these guys, they are molecules because it meets the basic definition of two or more atoms. But all these guys down here are also elements. So all these guys are elements. They are not compounds because they are not two different elements together. So all these guys would be elements. They would also be molecules because they're made up of two, but they are not compounds because they're all made up of the exact same element. Now, if you had something like water, H2O, which looks something like this, if you kind of put it together. This is a molecule because it is basically two or more atoms together. This is also a compound because it is made up of hydrogen and oxygen, which are different elements that have come together. H2O, would it be an element? H2O would not be an element because it is more than just one element together. It's hydrogen and oxygen, so it would not be an element. So something like water would be both a molecule and a compound. Something like oxygen would be both an element and a molecule because, again, it's an element and it's only made up of oxygen and it's two or more atoms together. So you can think of a molecule as sort of a general definition of all you really need is two or more atoms. Could be the same, could be different, doesn't really matter. You could call that thing a molecule. And for a compound, though, it does definitely need to have at least two different elements involved for it to be a compound. Any questions on that there? That ain't gonna do me good. All right. Here are some symbols and their names. And I would say some of these symbols and names are derived from a wide variety of sources. They're derived from Greek, sort of historic, Latin names, locations, people, all these things. You know, for example, Cu is copper, right? Fe is iron. Na is sodium. K is potassium, right? So sometimes maybe the symbol doesn't seem like it goes with the name, but there are reasons for why they are the symbols that are used. Lead, we do come across, which is Pb. Silver, which is Ag. Gold, which is Au. So you should do your best here. You should start learning the symbols and the names that go with them. They will not be provided for you, the names, so you do need to be able to recognize the symbols and the names. It definitely will help you out in the next chapter when we start talking about naming. So there's a lot of rules when we name things, so you don't want to still be sort of struggling of, what symbol is this or what name it is. So here are some, and again, your book does have obviously a table of them. Carbon is C, S is sulfur, N is nitrogen, H is hydrogen. Cobalt, helium is He, neon is Ne. And again, the rule, as we talked about there, capitalize if it is one letter, definitely capitalize, and lowercase if it is two, so you do not run into our cobalt carbon monoxide situation. Here's some other ones as well. Aluminum. Tin is one. Tin comes up a bunch, and that is SN is actually tin symbol. Se, which is selenium, my favorite element. Doesn't really come up a lot, but I like it. So that is also one that we do see. I would say, let's see here, chromium as well. So, a lot of these you will become familiar with as we go through the chapters, but I would take some time to sort of look over the periodic table, maybe this table that's in your book. Now, when you kind of look over the periodic table in terms of, what part of it, what you need to know, I don't know if this will really sort of help you out or not, but, for the most part, kind of to the left, and there's usually a staircase that comes down on the periodic table. Definitely above the staircase are very common symbols that we see. Probably the first two rows there and some of the stuff down here. The bottom two rows, we don't really run into too much of those guys, and kind of in the bottomish area of the periodic table, we really don't run into too much of those guys. So you'll probably get a handle of some common ones as we go through it, but usually kind of towards the top and kind of both sides, right and left, and a little bit underneath that staircase is, sort of where we will see a lot of symbols sort of pop up. I would point to that, but I frankly can't see that periodic table. I don't know about you on that wall. When I started teaching in here, I was like, the only chemistry class, it's all physics, obviously, and everything. So they're like, we should put a periodic table up. So that was the one they chose. I personally can't see it from where I'm sitting either, but All right. So again, make sure you do write those symbols. And again, this is really where some of the symbols do come from, some of the like Latin names and stuff like that. All right, so let's take a look at some of these. We want to write the correct symbols. So iodine is I. Yeah. Iron, as we talked about, is Fe. Magnesium is Mg, not to be confused with Mn, which is manganese. So they kind of sound similar. So that's manganese. We have zinc, which is Zn. And we have lithium, which is Li. So again, capital L, lowercase I in each of those cases. Any questions on that there? So we want to do some of these names here. So P is phosphorus. Ar is argon, which is a noble gas. Mn, as I just said, is actually manganese. Be is beryllium. And K is potassium. So we'll get some of those there. So you will be provided a periodic table. The periodic table will obviously have the symbol only. It will not have any element names. So again, you do need to be able to recognize these things. And again, you know, like I said, sort of invest some time now. It will make when we get to naming a little bit easier as we go through those rules and stuff like that. All right, any questions on symbols or elements, molecules, or compounds? So let's talk a little bit about the structure of the atom itself. So as I mentioned before, all the elements, really the basic unit of them are atoms, which are really, really small. And atoms do contain subatomic particles, as we were talking about a little bit earlier. And those subatomic particles are our protons, which again are positively charged, our electrons, which are negatively charged, and as I mentioned earlier, our neutrons, which all have no charge associated with them. There was a lot of sort of experiments that were done over the years that really sort of investigated each of these parts of the atom. What helped us understand a little bit better about electrons, protons, and neutrons, and also sort of where they are in the atom and sort of the overall structure of the atom. So when we look at sort of where things started, one of the earliest sort of ideas or try the explanation of what an atom is came from a guy named John Dalton. He developed sort of what is referred to as Dalton's atomic theory. Now, part of Dalton's atomic theory, and as we were talked about, I think in chapter 1, the idea of a theory is it may not always be correct in all aspects of it. Later experiments and stuff may prove that some parts may be right, some parts may be wrong. And that's what happened with Dalton's atomic theory. So he came up with the idea of how atoms sort of work. And as things went on, some of the parts of his atomic theory were found not to be so correct. So let's take a look at some of the parts of it. He said that really all matter is made up of these tiny particles, which he called atoms. He said that all atoms of a given element are identical to one another, and they are different than other elements. He said that basically atoms combination with one another in a chemical reaction, and really what will happen is just a rearranging of those elements. So we're not going to really lose anybody along the way. Bonds are broken and new ones are made. He also said that atoms are made up of two or more elements together, make up a compound, as we've been talking about. And the compounds is always made up of the same kinds of atoms and of the same number of each atom. That means obviously if you have water, it's always 2 hydrogens for 1 oxygen is basically what water is. Basically 18 grams of oxygen for every 1 gram of hydrogen that is present. One other thing as well, as you may know or may not know, the elements that make up a compound you have usually very different properties than the compound itself, right? So if we think about something like sodium chloride, that is basically salt. Salt has certain properties that would make you perhaps want to put it on your fries. But you wouldn't want to put up on your fries probably the components that actually do make up something like sodium chloride. That would be like a piece of sodium metal and like, you know, toxic green chlorine gas. But through the miracle of chemistry, right, it comes together and makes a salt, which has very, very different properties than the 2 elements that make them up. We could also go from compounds back to elements by some type of chemical reaction. We could break them back apart into those things. So the couple of parts of sort of Dalton's atomic theory that were found later on to be not so correct. One part is sort of this one right here, that all elements or atoms of a particular element are identical to each other. The existence of what are referred to as isotopes basically sort of disproves that idea. And what isotopes are, and we'll touch upon it here in this chapter, isotopes are really the same element, but they have different masses. So obviously, if they are the same element, but they have different masses, those atoms are obviously not identical to each other. They have some different particles involved and stuff like that. So that's one part of Dalton's atomic theory that's no longer sort of valid. Also, the idea that atoms are sort of indestructible. as well. That's another one where, it sort of falls short. In normal chemical reactions, we pretty much just play with chemical bonds and electrons. And that means that if we start with like 6 carbons, we will end with 6 carbons. They'll just be in different compounds on the other side of the reaction. But something like that, for example, a nuclear reaction, you can actually change the element from one element to the next. So by changing protons and neutrons and stuff like that. So those are the main points of Dalton's atomic theory. And this was a good sort of starting point, if you will. A lot of experiments afterwards again showed that atoms, although really small, do contain those subatomic particles, including our protons, neutrons, and electrons. And the idea is these guys do have charges. And one really important aspect of chemistry is the idea of opposites attract, right? So much like in life, opposites attract, right? As we move away from Valentine's Day here, right? So opposites attraction. Oh, wait, hang on, just attract. Maybe there's some attraction. So things that have opposite charge, like things that are positive and negative, they are attracted to each other. Things that have the same type of charge are repelled by one another. So much like in life, if you get 2 positive people together, that doesn't sound like fun, right? That's too cheery, right? And if you get 2 negative people together, also maybe not a good day as well. So right in life, we want to balance each other out, right? Somebody's positive, somebody's somewhat negative, right? You meet in the middle, everything works good. So in chemistry and really in sort of understanding the nature of the atom, they really use this sort of idea that these particles have charges to sort of their advantage, because if something has a charge and you throw like an electrical field, for example, in there, and an electrical field has a positive side and a negative side, things that have charges would be attracted to it or repelled by it. So for example, if you shot a beam and it kind of tilted upwards towards the positive plate, you could probably make a pretty good guess that that beam is positive or negatively charged, has no charge. It would have a negative charge because it bent up towards the positive, right? So opposites attract. If you shot like a beam and it ended up kind of bending towards the negative side of the electrical field, you can make a pretty good guess it would have the opposite charge. It would be something that is positively charged. And frankly, if you just shot something and it went straight and wasn't affected by the electrical field, you could probably make a pretty good guess that it has no charge. Yeah. So using electrical fields and even magnets, which has like a North Pole, South Pole, kind of works the same way. They were able to really sort of explore the nature of electrons, protons, and neutrons, and really atoms in general, and do some experiments that take advantage of things that have charges. There it is. There's my positive negative talk right there. I was just a little early, apparently. So again, taking advantage of those things with charges helps us really understand it. One of the earliest sort of experiments into really electrons was done by a guy named Thomson. And electrons, which are negatively charged, Thomson used what is referred to as a cathode ray tube, sometimes abbreviated CRT. Perhaps you might be familiar with them, maybe. If you have maybe an older TV that has a big back on it, yeah, it has like a picture tube in it, not like the flat screens. Yeah, they used to be sitting on the floor or up on the shelf and stuff like that. Our computer monitors, which actually have like the big back out of it, again, not like that one. But those all have picture tubes. Those are all CRT tubes in there. If you're not sure what a TV with the back has it, you used to call a TV repairman to come fix it. You open up the back of the TV. I know there's a guy came to your house. He adjusted your picture tube. I know you didn't just run to Costco and get a new one when it stopped working, right? And throw it in your back of your car. But those all had cathode ray tubes in it. And basically what a cathode ray tube is, it's really like a tube, and it really shoots these negatively charged particles like electrons. And it also would take advantage of the sort of charge. So it would have a positive side and a negative side. So this beam of negatively charged particles would be attracted towards the positive side of the tube. And a lot of times what they would do is put something on the tube that would sort of fluoresce as the beam hits it. You could actually see where the beam is and stuff like that. So Thomson did a lot of work with electrons and the CRT tubes, and he was able to come up with the charge to mass of an electron. And after Thomson, there was another kind of important experiment in terms of the electron, and this was one that was done by a guy named Millikan. He did what was known as the oil drop experiment. And basically, it is kind of what it sounds like. It was a chamber where it also had an electrical field sort of in the chamber. And what he did is he took oil droplets and he basically heated them up and dropped them in. There was like a little opening in the tube here. And when the droplet would start to fall by natural gravity, it would pick up a charge. And what he was able to basically do was he was able to adjust this electrical field in such a way that pretty much the oil droplet just kind of hung there. It basically was able to be suspended. And the result of Millikan's sort of experiment was he was able to come up with really what the charge of an electron was. So both Thomson and Millikan, taking their experiments together, allowed us to figure out the mass of an electron. And the mass of an electron is something like 9.09 times 10 to the minus 28 grams is the mass of an actual electron. Is that a large number or a small number? It's a really small number. You're going like 27 places to the left and put in a bunch of zeros, basically, right? So it's a really small number. So that was a really major sort of outcome in sort of the understanding the nature of electrons were these two experiments. And those experiments, it was always believed that the atom was basically neutral. So they sort of discovered electrons first, which have a negative charge. So the belief was that the atom had to have something in it that was positively charged to really balance it out. And one of the earliest sort of models of the atom is the one that we see here in this picture. This is what is sometimes referred to as the plum pudding model. Plum pudding's like rice with like raisins in it. And basically the idea was you have this sphere of positive charge. So the positive charge was spread out all over this sort of sphere. And embedded inside of the sphere were negatively charged electrons, which are these guys. So these negatively charged electrons were embedded inside. And they felt that most of the mass of the atom was the electrons. So this is one of the earliest models of the atom, one proposed by Thomson. Basically a sphere of positive charge. We have these electrons embedded inside like his raisins and his dessert. And most of the mass of the atom was made up of the electrons. And this was sort of an accepted model of the atom until really the next sort of big experiment that sort of happened. And that experiment was one that was done by Rutherford. And Rutherford did what is known as the gold foil experiment. And Rutherford used what are known as alpha particles. And alpha particles are positively charged radioactive particles. There's also beta particles that are used in a lot of these experiments, which are negatively charged, and there's gamma particles, which have no charge. So those three particles are very commonly used in experiments because they kind of simulate electrons, protons, and neutrons having the same sort of charge. Now, when they shot these alpha particles at pieces of gold foil, which is basically just atoms of gold foil, basically atoms of gold there, what they expected to happen based on the plum pudding model was they're shooting these very heavy, positively charged and moving really fast particles at basically a big circle of positive charge. So kind of like, you know, if we held both sides of this paper and we shot a pin at it really fast, it probably would punch through, right? But there would be some deflection that would occur as it punched through. And what they expected to happen were these particles to go through, but that there should be obviously some deflection between the positive and the positive that it's going through. And this is really what they actually thought was going to happen. What they actually found when they did this was, and they shot these alpha particles in a setup such as this, where they have alpha particles here shooting out. This is a detection screen where you can see where it's hitting. What they found was pretty much most of them kind of sailed through with no problem. So they just went right on through, nothing bad happened. But what they did see was every so often they would see an alpha particle scattered at a really big distance. It would kind of ricochet off at these really, really big angles. So this was quite surprising to them based on the model of the atom, where they expected kind of all of them to go through with some deflection. So we need to account for really what they saw. If something went right through and didn't deflect or anything, did it hit anything? It didn't, right? So like if I threw my pen, there's nothing in the way. It's just going to go right on through. It's not going to run into anything. And that would explain why these particles went right through with no problem. It pretty much hit empty space. Now we have these positively charged alpha particles that eventually get banged off in these really long directions, even come back to the source. In order to make something heavy like that, that's moving really fast, bounce off, it would have to hit something that was very much what type of charge? If the alpha particles are positive, it has to hit something that is very, very densely positive to make that. So the particles where we see sort of bounce off at really large angles had to hit something that was really densely positive. So what this led them to understand was maybe this is not so correct of a model of the atom. And they had to sort of revisit the idea of what the atom looked like. So, you know, if this was all my positive charge, like we said before, and we did it and it popped through, if I took all my positive charge, right, and because I want to keep them, I'm going to take a handout to do it that way. If I take all my positive charge and basically fold it, right, down, not all spread out all over the entire circle, but if we sort of concentrated it all down here, how many times can you fold a piece of paper before you can't do it anymore? Like 7, I think, right? And then you run out of product. So let's just say instead of positive all over like this is just my positive charge, right? So when I would take my pen and try to punch it through, I'm going to have some problem, right? It's going to bounce off like that. And that's what we had to see happen here in this experiment. So they came up with sort of the model of the atom based on this, and they said that the atom was mostly empty space. And that accounted for all of those rays that basically went through with no problem. It did contain a dense positive core, which they call a nucleus. And later experiments and such found that inside the nucleus is where we have our protons. And also later experiments like in 1930s, that is where we have our neutrons. So in 1930 or so, neutrons were discovered to be within the nucleus as well. They also felt that most of the mass of the atom was actually the nucleus. And that really does make sense, because out of protons, electrons, and neutrons, the neutron is actually the heaviest of all of them, followed very closely by the proton. And both protons and neutrons are about 1,830 times heavier than any electron. So an electron is about 1,800 or so times less massive than a proton or a neutron. And lastly, here we have our electrons moving in the empty space. So this really is sort of the modern version of the atom that came out of these experiments. Basically, mostly empty space, has a really positive core, which is known as a nucleus, where we have protons and neutrons, protons being positively charged, neutrons having no charge. And flying around the nucleus at some distance is our electron. So we have this protons, which are positively charged. We have our neutrons that have no charge in our nucleus. and we have these electrons, which are negatively charged. Electrons, which are negatively charged, will they be attracted to the nucleus, which is basically positively charged? There is, and that's what kind of keeps the electrons there in most situations. There is some attraction between these two, which allows the electron not just to fly off, it's kind of attracted and held there by that attraction. By the way, again, electrons do not move in pretty circles. They move, pretty randomly about the atom. They do not move in circles or anything like that. Even if biology tells you that, they do not. They actually move pretty randomly about the nucleus. You actually do not know at any given point in time exactly where the electron is. The best you could do is go, I think there's a pretty high probability that an electron will be in this area of the atom. And usually the highest probability in a lot of cases is near the nucleus because of the attraction between the positive nucleus and the negatively charged electrons. Question on that there. All right, so there is maybe a prettier picture when I drew, maybe not, I don't know. But again, we have our protons and our neutrons that are in the nucleus, and our electrons moving around in that empty sort of space, attracted to the nucleus, can't really get away as well. All right, so one unit of sort of measurement of mass for an atom is what is referred to as the atomic mass unit, and that is also abbreviated as AMU for atomic mass unit. It is actually the numbers that you see on the periodic table on the bottom. Those are an atomic mass unit per atom. And we can see here a proton's 1.007. The neutron just barely beats it out at 1.008. And much, much lower in terms of the mass is our electron at a 0.00055 AMU. So we don't use AMU a lot. We use grams, and we'll talk about that in a later chapter, but this is one representation of it. And you can just see by the numbers, the mass of an electron is much lower than both the proton and the neutron. All right. So which of the following subatomic particles fits each of the descriptions found outside the nucleus? Which one is it? It is the electron. Has a positive charge is the proton, and has mass but no charge is neutron, which, as I mentioned, was discovered in 1930, in case you're curious, by a guy named Chadwick. He did a lot of experiments with things that resembled like X-rays. They kind of have no charge, and sort of discovered the existence of neutrons. In each of the following, true or false, the mass of an electron is greater than the proton. That is false. The electron is the least massive of all of them. Protons have a positive charge, electrons have negative. Yep. The nucleus of an atom contains only protons and neutrons. That is true. Yeah. So again, those are the subatomic particles in there. Pretty much all elements will have protons, electrons, and neutrons, except for our good friend hydrogen. Hydrogen actually only has a proton and an electron. It does not have a neutron. But everybody else, every other element will have all three of those guys present. All right, so there's a much nice one. So this is sort of the idea of an atom, and although an atom is really small, the nucleus is actually even smaller. You could think of like the atom as like a big football stadium, if you will, and like the nucleus is like a marble on the 50-yard line in the middle. Yeah, so that's sort of the relationship. Everything else is kind of the empty space where electrons would be flying around and stuff like that. And that's what we see here. As we talked about, the electrons not moving in pretty circles, but this is sort of what is sometimes referred to as an electron density. I don't know how well it comes up on the screen-ish, maybe-ish. But there is some various shades of blue here, and that's sort of the probability map of where you can find an electron. So usually if you see something like that, the darker areas are higher probabilities of finding electrons. And as you kind of fan out from the nucleus, it usually gets lighter and lighter, where the probability of finding an electron gets kind of lower and lower. Yeah. It is essentially, yeah. So this is sort of that sort of bluish area. Sometimes, a lot of times it's red. Can't really see much of the bluish area, but sometimes it's red as well. But that's usually the electron cloud is kind of where those electrons are. And that's basically in that empty space. And again, they are traveling, randomly about, in this area. All right, any questions on the atom? So you need to know a little bit about the experiments that led us to understanding the particles, where they're located, obviously, the modern version of the atom, right, which is mostly empty space, nucleus, where protons, electrons, and neutrons are found. Any questions? All right, we're going to talk about some other aspects of atoms, and these are atomic numbers, mass numbers, and isotopes. We will start with the idea that really the chemistry of atoms do come from electrons. They're involved in all the combination of molecules and really the differences there. In a basic chemical reaction, which is pretty much what we deal with in this class and most chemistry classes, really the only thing that happens is we have the left-hand side of the arrow, which are reactants, and that's our starting material in a chemical reaction. And on the right-hand side of the arrow, we have products, which are obviously what are formed as a result of the reaction. But basically what happens in a chemical reaction is everybody that's on the left-hand side, they pretty much break all their bonds. And then all the elements reassemble on the right-hand side and they make new bonds. And as a result of recombining sort of a different configuration, they end up having different compounds and substances that are formed on the right-hand side of the arrow. Absolutely nothing in a normal chemical reaction involves what's in the nucleus. So protons and neutrons, they are not involved in any type of normal chemical reaction. It is really just the electrons. And as we'll talk about in later chapters, there's specific electrons that are involved in those sort of bonds being made and bonds being broken. The only situation where the nucleus and our protons and neutrons get involved is if you do some type of nuclear reaction, which since we're skipping chapter 5, we're not going to do that. But that's the only time that actually protons and neutrons get involved if it's a nuclear sort of reaction. But in a normal chemical reaction, like we talked about in this class, it's all about the electrons. So that's important. So one number that's really important is what is referred to as the atomic number. The atomic number is the number of protons there are in the atom of a nucleus, or the nucleus of an atom. I'll spit that out, right? The atomic number is sometimes abbreviated with a Z. Now, if we have a neutral atom, right? If something is neutral, it basically means it has no charge. So if we know the number of protons which are positively charged, and really the only thing else in an atom that has a charge is the electron that's negatively charged. If we have something that is neutral, the atomic number will also tell you the number of electrons that you should have, because all the positives and all the negatives should balance each other out. It's important to know, though, if you're asked a straightforward question like, what is the definition of the atomic number? The definition is just protons. So second to that is the information that you could get if it's neutral is they will also tell you about the electrons. But the actual definition of atomic number is only the number of protons it will tell you. Now, if we go to the periodic table, our good friend, the periodic table there, and we look at something like our friend oxygen, and we see a number above the symbol, that is the atomic number. So when you look at the periodic table and you see the number above the symbols on all of them, and a lot of periodic tables, it's directly above the symbol, but sometimes it's up and to the right. But any number above the symbol on most periodic tables should be the atomic number. If you look at a periodic table that maybe you have near you, or if you can see that one, if you have good eyes, if you look at the periodic table and you look at all the numbers that you see up on top for all the elements, do any of the numbers repeat? They do not. They actually kind of go in order, 1, 2, 3, and they kind of keep going across and stuff like that. None of the numbers repeat, and that's a really important aspect of atomic number, which is the number of protons. That means that if you know the number of protons are the atomic number, which is basically the same thing, you will know what element you are referring to, because every element has its own unique atomic number. That means that out of protons, electrons, and neutrons, the subatomic particle that's most important in terms of determining the element is the protons. So if you change the protons, you change what element you're talking about. So you will never find a oxygen atom with 6 protons, because that has 6 protons is carbon. Yes. So it cannot be oxygen, because oxygen should always have 8. Carbon always will have 6. So it's a really important thing. Periodic table, all you have to do is find the appropriate atomic number of protons, and you'll know what element you're talking about. That means, for example, here for our oxygen here would have 8 protons. And if it was neutral, it would also have 8 electrons, which gives you a grand total of no charge, right? 8 positives, 8 negatives equals 0. So that would be a neutral oxygen atom. Same thing with carbon. If our carbon was neutral here, we would have 6 protons, which are positively charged. And to balance it out, we would need 6 electrons to also balance it out to give us no charge. So once again, the atomic number of protons, but outside of that definition, if it's neutral, it will also give you that other piece of information, which is how many electrons there should be. Nitrogen's atomic number, if you look on the periodic table, is 7 above it, above N. And again, that means in a neutral nitrogen atom, we have 7 protons and also 7 electrons. Any questions on atomic number? Yeah. Neutral means it has no charge overall. Yeah. So when we talk about an atom, there's really 3 things in an atom. If this is my atom, there are protons that are positively charged, there are electrons that are negatively charged, and there's neutrons that have no charge. So because the neutrons really have no charge, they're not going to really do anything with anything about a charge. So what that really means is if it's neutral, the overall charge of that atom is 0. And that means that it has to have the same number of protons and electrons. However many positive protons you have has to be how many negative electrons you have, and they have to equal each other, and that will give you 0. Just mathematically, you know, if you had 8 positives and you added it to 8 negatives, it's basically 8 minus 8, and that equals 0. And overall, it has no charge. Yeah. Other questions? Another important number is what is referred to as the mass number. The mass number is sometimes abbreviated with an A. And the mass number is the number of protons and the number of neutrons there are in an atom. And the atomic number are important because if you use them together, so for example, our mass number is the number of protons plus the number of neutrons. Our atomic number that we just talked about is the number of protons, which means if I take both of those numbers and subtract, the number of protons will cancel, and that will give me the number of neutrons. So if you take the mass number minus the atomic number, that will tell you how many neutrons there are in a particular atom. As I mentioned earlier, except for hydrogen, which hydrogen again only has a proton and an electron. Hydrogen has no neutrons. All other elements will have all 3 of those particles, protons, electrons, and neutrons. When you calculate the mass number, or you calculate the atomic number, or frankly, you calculate how many protons, electrons, or neutrons there are, which you will do, they are all going to be positive whole numbers. So they all should be positive whole numbers. So that brings me to the question of, not sure what my question is. Let me think about my question now. Here's my question. I go to the periodic table, I see 7, and I see like 1401 underneath nitrogen. So we know this is the atomic number. Is the bottom number the mass number? No, right? So let me reread the bottom line. All those things, the mass number, the atomic number, the number of protons, electrons, and neutrons, they all need to be what type of number? Positive whole numbers. Yes, no decimals. Yeah. If you look at a periodic table, again, I recommend one near you because you probably can't see the numbers on that one. If you look at all the numbers that come underneath all the symbols, they pretty much are all decimals. Yeah, there is no whole number that is on there. So what you actually see on the bottom there is not the mass number. So let me write that. That is not the mass number. What this actually is, this is what is referred to as the atomic mass, which we will talk about in this chapter as well. That is the atomic mass. That is not the mass number. So you can only find the atomic number on the periodic table. If you need to calculate the mass number or the number of neutrons, protons, all those things, you will be given enough information in the problem to do so, and they always should be whole numbers. So if you find yourself, don't find yourself there on a test or a quiz, starting to write the number on the bottom there, right? So if you find yourself doing that with some decimals for the mass number, you really should lay up a big X on that before I get to it, yes, and just mark it wrong. It will be wrong. What really does sort of get people is oftentimes the mass number and the number that you actually see on the periodic table, they're actually very close numbers. So sometimes people think, oh, it's just like the rounded version of, or the unrounded version of the mass number. But it really isn't. They are similar a lot of times, but not in all cases, but they are fairly similar because they are based on kind of that same idea, the atomic mass based on how many protons, electrons, and neutrons there are, but they are different. So never use the number on the bottom of the periodic table for the mass number. You should calculate it. You should have the ability to do so. Yeah. Is it? Well, nobody wants to update this computer. It's been here 40 years. Nobody wants to do that. Remind me later, like everybody else. There we go. All right. All right. So like I said, make sure don't use that number, but definitely use the number on top as the atomic number. It's not a problem. So let's talk a little bit about isotopes. Isotopes are the same element, but they do have different masses. And as we talked about earlier, one of the things that was sort of incorrect in Dalton's atomic theory, the existence here of isotopes, which are the same elements, but they do have different mass. So in order for them to be the same element, which particle has to be the same in all of them? Protons, electrons, or neutrons? Protons, right? Again, the proton determines what element we're talking about. So they all have the same number of protons, but what gives them different masses is they have different numbers of neutrons. So it's different numbers of neutrons. Also gives them slightly different properties as well. Now, one common way that we do write sort of symbols of isotopes is what we see on the bottom. This is the chemical symbol. And on the top left of the symbol, we put the mass number. And on the bottom left of the symbol, we put the atomic number. So for example, hydrogen has 1 proton and no neutrons. Deuterium, which is like heavy hydrogen, has 1 proton and 1 neutron. And tritium, which is like the radioactive version of hydrogen, has 1 proton and 2 neutrons. So if we were going to write the symbols for each of these isotopes, they're all isotopes of each other, and maybe you weren't sure what hydrogen symbol was or deuterium or whatever it is, you would look here and say it has 1 proton. You would go to the periodic table and find number 1, which will say H, and that's how you know what that symbol would be. So you would write H. Bottom left would go the atomic number, which we find on the periodic table. The mass number is the protons plus the neutrons. So we would take 1 plus 0, which gives us 1. And that would be the correct symbol there for hydrogen. 1 up on top for the mass number, 1 on the bottom left for the atomic number. Now, maybe we get to deuterium here and you're like, I don't know what that is. But once you see that it has 1 proton, again, all you have to do is go to the periodic table and find number 1, which is still going to be hydrogen, even though it didn't say hydrogen. And it will still have the same atomic number, which is 1 for 1 proton. But in this case, it is 1 plus 1 in terms of the mass number. 1 proton plus 1 neutron will give me 2 in terms of the mass number. And this symbol would be deuterium symbol. The first symbol would be hydrogens. And if we did tritium, same idea. Tritium, I don't know if that's hydrogen, but I do see it has 1 proton. So I go to the periodic table. Once again, number 1 there is hydrogen. And we would put the atomic number on the bottom. In this case, that is 1 proton plus 2 neutrons, gives us a mass number of 3. Yeah? So typically speaking, when you write these symbols like this, you take the top number minus the bottom number on the left there, and that gives you the number of neutrons. So for hydrogen on the far left, if you take 1 minus 1, that is 0 for the number of neutrons. For deuterium, which is the middle guy, you take the 2 on top minus 1 is 1 for neutrons. And for tritium, which is the guy on the left or on the right there, you take 3 minus 1, which would give you 2 neutrons. Question on that there. Now, another very common way that sometimes isotopes are written is something like this, Cu64. Good friend of mine, we use a lot, radioactive copper. This is copper 64. The 64, what number do you think that is? Is that the mass number or atomic number? Bless you. Well, I can know by going to the periodic table, right, and looking up copper. And if I go to the periodic table and I find copper, and above copper is the number 29. So that 29 should be what number? That's the atomic number, which means by default, the 64 would be the mass number. So this is another common way that sometimes isotopes are written. That would be the mass number. We could obviously get the atomic number from the periodic table. And if we wanted to write it in sort of our same formula here, we would write Cu for copper. On the bottom would be 29, which is our atomic number. Up on top would be 64, which would be our mass number in this case. Question on that there. That means that this isotope here has how many protons? Which one tells you how many protons? It is 29, the atomic number. So it would have 29 protons. This has no charge, which means how many electrons should it have? To equal 0, you would need 29, yeah? 29 positives plus 29 negatives, they all cancel each other out to 0, no charge. How about the number of neutrons in this case? What would it be? To calculate the neutrons, we take what number minus what number? Yeah, we take the mass number minus the atomic number, which in this case is 64 minus, what did I say there? 29. That's a lot of math. That like a 35? I didn't even pick up the calculator. I know I did too, but I did this example earlier today, so I still have the number in my head. No, I'm just kidding. Any questions on that there? All right. So let's take a look at some of these here. So take a moment here for each of these, calculate how many protons, electrons, and neutrons there are for each of these. Okay, let's take a look, see how we're doing. So once again, top number left is which one? That is the mass number, which is our protons plus our neutrons. Bottom there is going to be our atomic number, which is just our protons. So the number of protons here should be pretty straightforward. That is going to be 27, right? Which is our atomic number. Now, this does not have a charge, and I know it doesn't have a charge because, frankly, there's nothing written there. Yeah, so if there was a charge, there would be something written there like +2, -3, something like that. So since there is no charge, we could assume that this atom is neutral. And as we've been talking about, because it would be neutral, the number of electrons then should be 27 as well, right? So 27 positives, 27 negatives gives you no charge, which is essentially what we don't see there, I guess. Or no charge that's resonating there. Our number of neutrons would be our mass number, which in this case is 60, minus our atomic number, which is 27. So that looks like a badly written 33. There we go. 33. Any questions on any of those there? Next one is Cl, which is chlorine. Once again, there's nothing written here, so there's no charge. We do know from the atomic number, the number of protons here should be 17, coming from this number here. Once again, because it has no charge, it should be neutral, which tells us our electrons should match it at 17. Once again, giving us no charge overall, positives and negatives. And our neutrons would be how many? It'd be 37 minus 17, 20. Yeah. Any questions on that one? Lastly, U is uranium, I believe. There we go. And again, no charge there. So once again, looking at the atomic number first, that's going to give us for our protons 92 positive guys. For our electrons there will give us also 92 negatives to balance it out to 0. And our number of neutrons will be a lot 238, which is our mass number, minus our atomic number, which is 92, like a $1.46, maybe something like that. Yeah. Any questions on any of those? So again, you can see protons, electrons, neutrons, all whole numbers. Yes. Mass number on the symbol and atomic number on the symbol, all whole numbers. Any questions on any of those there? Okay, so I want you to try some here where you write the symbols. So write the symbols with both the mass number and the atomic number. If you've got a periodic table, it might be helpful here. So we're looking for krypton that has 48 neutrons. Nitrogen's got 6. And iron's got a mass number of 56. Krypton there on the periodic table. That is Kr, and that is a 36 above it. So obviously that would be a good start. The symbol. The other important piece of information we get from the periodic table is obviously the number that's above it, which is our atomic number, and that is 36, which then should go bottom left here. That's important because that 36 also is how many protons we have, which would be 36. And that's important because I want to actually calculate my mass number, which should be my protons plus my neutrons. So I know that will be 36 plus 48, which was given to us. So the mass number here should be an 84. Yeah. Any questions on that one there? Looking at the next one, which is nitrogen. So once again, we'll roll to the periodic table. We'll find N, which is nitrogen. We will see the number above it, which should look like 7 in this case. And that will tell us that we should start with N. And once again, our atomic number, which is 7, will go to the bottom left. And that 7 will also again tell us that is how many protons we have in this case. And that will allow us to be able to calculate the mass number, again, not using the number on the periodic table. That will be 7 plus 6, which will be 13, I believe. And that will give us a 13 up on top. Any question on those two? Lastly, here we have iron, which is Fe on the periodic table. So Fe. And iron's 26, I think, still. Haven't changed. That means that our symbol here would be iron. Our atomic number would be 26. In this particular case, they actually gave us the mass number of 56. So that is what should go up on top. They also wanted to know how many protons, electrons, and neutrons there are in this case. So our protons would equal our atomic number. Our electrons in this case, since it is neutral, should also be 26, right? So that they balance out. And then our neutrons would be our mass number, which is 56 minus 26, and that is 30 in this particular case. Yeah. Any questions on any of those there? So as you can see here, we calculated our mass numbers, did not use it from the periodic table. Just to finish on, what happens if something did have a charge? So if something did have a charge, things that have charges, those are what are referred to as ions. So ions are things that have charges. There's really two types. There's a cation, which is positively charged, and there are anions, which are negatively charged. So when something does gain a charge, we do have to adjust a couple of these numbers here. So let me go this way, actually, and let me get rid of some of this here. I got somewhere to scribble on. I'm gonna keep those bottom ones. All right, so let's say that we take our same nitrogen that we have below us and we did before, and let's just say we had our 13,7 nitrogen, but it had a -3 charge here. So in this case, it has a -3 charge. It's a negative charge, so this is what's referred to as an anion. It has a negative charge. So the number of protons here would be how many? It is 7, right? Now, because it has a charge, can I change the protons to get me to the right number? Would I want to change the protons in this case? No, because if I change the protons, it will no longer be nitrogen, right? So you'll change the element. So when things gain charges, it's not the protons. They do remain the same. So it is actually the electrons that change. So it's those negatively charged guys that actually change. So in this particular case, how many electrons would I need to end up with a -3 overall charge? I would need 10 electrons, yeah? If you have 10 negative things and you have 7 positive things, you have 3 negative things left over. So basically, that is where the -3 comes from in the charge. Basically, it has 3 more electrons than protons. So each electron and proton basically cancel each other out. So 7 of them get canceled out, but now we're left with just 3 extra electrons that have a -1 charge each, and that's how we get to the -3. The neutrons here would be the same. It would be 6. It would still be 13 minus 7 in this case. So this is an anion. Now, what is the difference between the number of electrons here and the electrons in our neutral guy, which would be 7? Did I have more or less electrons? There is more electrons, and that's how something becomes an anion or negatively charged. It actually will gain electrons. Because it has extra electrons, that's how come it has extra negative charge. So when you see something with a negative charge, the first thing you should realize is it's gained electrons. The actual number on the charge is actually how many electrons it gained from the neutral guy. So this has a -3 charge. Neutral guy had 7. It gained 3. This guy has 10 electrons. That's how you can figure it out. You basically take the atomic number and add 3 to it, and that will tell you the proper one there. Question on that there. Now, what happens if I take my iron that's on the bottom there and I give it a +2 charge? How many protons would this iron have? It will have 26 positive charges. How many electrons will it have? It will be 24 electrons. 26 positives and only 24 negatives leave you 2 positives left over, right? And that is where the charge comes from. It's because in this case, it actually has more protons than electrons. So it's only got 24 electrons to cancel out 24 protons, leaves you 2 protons by themselves, if you will, in that sense. They're all still there, but you have 2 protons that are not matched up, and that will give you your +2 charge in that case. Now, when we compare it to the electrons in our neutral guy that had 26, the one with the positive charge had more or less electrons? Less. And that's what happens when somebody becomes positively charged. They have more positive protons than they do negative electrons. So something that becomes a cation is a result of losing electrons. So when something gains a charge, the only thing that changes is the number of electrons. And if it's a positive charge, that means that it has lost electrons. And the number of the charge is how many electrons it lost from the neutral. So our neutral guy had 26 electrons. This guy had a +2, plus lost 2 electrons, drops to 24. And that's how you can figure it out. Any questions on that there? All right, we will lay it up there for today.